Calendar really quickly. So we're going to cover 2.2 today. I think I mentioned in that video that I had you watch, I normally give you 2 days to do homework assignments. So 2.1, we finished that yesterday. It's due on Wednesday. So at the beginning of class, make sure that you've got that done if you have questions. Again, office hours are before class on Tuesdays and Thursdays. So if you've got a question, come and see me then. If you want to see me another time, that's fine, but just send me an email or call me or something and we'll work out a time. And then at the end of class, I'm going to talk about representative problems. I mentioned those in that video that you watched. Next Tuesday, so a week from today, the representative problems from 2.1 through 2.3 are due. So I showed you what those are, and we'll talk about those real quick at the end. Any questions there? Okay. All right. Then let's take a look at, so this section is on limits of functions. And we're slowly going to go from very informal definitions of what a limit is to make them more precise toward the middle of the chapter and toward the end of this week. So yesterday we were using the word approaches or gets really close to or arbitrarily close to is the word that we talk about a lot of times. So we're going to start off by defining what a limit is in kind of an informal fashion, get used to the notation and that sort of stuff. Several of these are going to be done graphically. Some of them we're going to use some algebraic expressions and stuff like that. This is kind of getting your feet wet in terms of, yesterday we did a bunch of numeric stuff, plugging numbers in calculators, making guesses and stuff. Here we're actually going to compute them either by looking at a graph or doing them numerically. So let's look at what the definition is. Yeah, they're right there. Yep. So I'll put them on that desk at the beginning of class, so grab one on your way in if you want them, okay? So it says, suppose f is defined for all x's near a except possibly at a. We'll come back to that in a few minutes. Okay, if f of x is arbitrarily close to L, so when we say arbitrarily close to L, we mean as close as we want to get to that, as close as we'd like, okay? For all x sufficiently close but not equal to a, so very wordy definition here, we say the limit as x approaches a of f of x is equal to L. So the limit as x approaches a, so as the x values get really close to this a value, okay, then f of x gets closer and closer to this limit of L. And we write it like this, and this is how it's said. So this is said the limit as x approaches a of f of x is equal to L. Now this point right here, this a where we're trying to find the limit, we call that, or I like to call it, the point of interest. That's where we're trying to find the limit. This is, of course, f of x. It's the function. And that big capital L, we don't just randomly choose variables. A lot of times we want them to represent what we're looking for. That is the limit, okay? So a is the point of interest. That's where we're trying to find the limit. F is the function that we're working with, and L is the limit. So these are x values right here, and this is a function value. It's a y value, okay? All right, so let's take a look at a graph. Limits are really easy to find if you've already got a picture for it. So here's what this says. And the software that I use to make these, it should normally put them underneath. That's the standard way to write them. The software that I use, it's just the equation editor in Word. It kind of puts it off to the side. So just realize that just slide it right underneath there. So this is the limit as x approaches 1. Kind of nice that we can just read it from left to right. Of f of x. Let's look at the graph over here. What is our point of interest? 1. So the x values that we're interested in approaching are 1. So I'm going to use red here. So we're interested in approaching 1 from either side, from the left and the right side like we were doing yesterday. And we're interested in finding the limit. The limit is a function value. So if we look up here, the function values are getting closer and closer to this point as we come from the right. And from the left, they're getting closer and closer to this point. Okay? So what's the limit here? 2. Okay, the limit is 2. It's approaching 2 from both sides. The function values are approaching 2, okay, from above here and below here, as the x values get closer and closer to 1 from either side. If we take a look at the limit as x approaches 2, the point of interest is 2. So we're interested in what happens if the x values get really close to 2. What happens to the function values? Well, they get bigger here and they get smaller here. So what's the limit? The limit is 3. Okay, let's do the same thing. If we're interested in the limit as x approaches 3, what's our limit here? What does it look like it's approaching from either side? It's approaching 4. And what about the limit as x approaches 4? We'd have to kind of guess, right? Maybe 4 1/4, maybe 4.25 or somewhere around there. And we'll just say approximately. Okay, now you'll notice that in each one of these cases, they're handled a little bit differently. Okay, the picture looks slightly different. You'll notice that at 1, the function value was in fact 2. This is a closed circle right there. They were kind of emphasizing that. You'll notice that at 2, we have an open circle, and the function value is actually up here at 5. You'll notice at 3, we have an open circle right here for the function value, and there is actually no function value. The function isn't defined at x equals 3. And you'll notice we didn't even write one. Okay, we just had a point on the graph, and we kind of estimated where it was. Okay? And this brings a really important part of limits to mind. Okay, the limit has nothing to do with the function value at the point of interest. So we really don't care that the function value right here is 2. We don't care that it's 5 up here. We don't care that it doesn't exist right here, and we don't care that it might be exactly 4.25 there. Okay, what we care about is what's happening around the point of interest. So limits don't have anything to do with what's happening at the point of interest. Limits are just what's happening around as we approach the point of interest. The function can be defined, it can be somewhere else, it can be not defined. It doesn't affect the existence of a limit there. Okay? Any questions? Okay, so we're going to take a look at a couple of others graphically, and we're also going to use a table, and I'm going to produce those on the calculator. So if you want to just watch for the time being, here's what we're going to do. Clear this off. I'm going to go to the y equals menu, turn my stat plots off. I'm going to type this function in right here. So this is sine of x divided by x. You might want to think about where we're trying to find the limit and if we have any domain issues there. And then the next one is the cosine of x minus 1. And then we're going to divide that by x. And you'll notice that on both of these, we're trying to find the limit as x approaches 0. Okay? So I'm going to do this. First of all, I'm going to make sure I'm in radian mode. So I'm in good shape there. And then I'm going to set up the table. And I'm going to do negative. Let's see, I'm going to do this. I've got it on ask. We'll just do 0. Okay. So we're going to take a look at the first one. So I'll turn this one off. So here's the table. Okay. Now, it's already got some values in here, so I'll clear those off or delete those. Okay. On this first one, what's the point of interest? 0. What happens if I plug a 0 in? Okay, it's undefined. Okay, I want to plug in numbers that are really close to 0. So let's plug in 0.01. Let's plug in 0.001. Okay, now, calculators are interesting, and I'll mention this a little bit later. Okay, this looks like it says the answer is 1, right? If I hop on there, look down below. It's got, what, 6 9s and then an 8? So it displays a 1 up here. You can't rely on that because it's kind of rounding, it's truncating and doing some other stuff. So you've got to be careful when you use a calculator for these. Okay, but that's getting really close to 1, right? So what would you guess the limit is as x approaches 0? You'd guess it's 1. Should we leave it like this and just rely on the calculator like that? Just numerically? We should do at least one other thing. Let's plug in some numbers that are really, let's plug in some numbers that are really close to 0 from the negative side. And I'll even throw in a couple of these. Pretty good evidence there. Let's check and see what it is. In fact, that's so close, okay, it actually has a bunch of 9s there, but it's so close it won't fit them on there, so it's going to round up to 1. Okay, so is that pretty good evidence that coming from either direction we get a 1? Okay, let's do one more thing. I'm going to hit, I'm going to hit zoom and let's see, let's do zoom 4. that look pretty good? Okay. Anybody worried about this point right here? I mean, does it look like it's approaching 1 from either side? Okay, and we could hit trace, and notice there is actually a hole. It knows there's not one there. Okay, at point 1, we've got 0.998, and at negative point 1, we've got positive 0.998. Pretty good evidence. Okay, so if we drew a picture of it, it looks something like this, and the limit here is 1. Okay, the next one I'm just going to do using a picture. So we're going to turn this one off and turn that one off, and then we'll just hit graph and see what we end up with and see if we can tell. So the graph looks something like this. Is that right? There better be a hole. Okay, so let's take a look. I'm going to hit trace. There is a hole. If I go over a little bit, I get negative 0.049. If I go over a little bit, I get positive 0.049. If I were to go over to here, and let's say this is, if you didn't know, your calculator will do this. This is just jumping from pixel to pixel in the decimal window. If I were to type in 0.01, it will actually go and find that point. If I type in negative 0.00001, it will actually go and find that point. And notice again, it doesn't actually have a function value of 0, but it would be rounding. Okay? And if you did this on the home screen, it would have more places to put the decimals. Okay? So we've got an open circle right here. Okay? But what would you guess, based on what we've seen so far, that the limit is for this particular function as x approaches 0? It's going to be 0. Now, these are two limits that come up quite often in calculus. You're going to want to put those in your bag of tricks. This one in particular, sine of x over x as x approaches 0, that limit is 1. Okay? All right. Now, usually when we find a limit, we're finding what we call a two-sided limit. But we want to define what it means to have a one-sided limit. So we're going to talk about a left-hand limit and a right-hand limit. And there's really not a whole lot to fill in here. Okay, and this is what it means. The limit as x approaches a from this little, looks like it's in an exponent place. All it's indicating is we're approaching a from the right or from the positive side. Okay, so from the positive side. We're only interested in what it's approaching from the right if it's a right-handed limit. And on this one, we're only interested in what it's approaching as we come from the left, from the negative side. Okay? So if you flip the page over, I've got several examples of one-sided limits. So it says, given the graph of g of x, which is over here, and again, it's really nice if all you're given is just a graph and asked to find what the limits are, because you can usually just look at it. So the limit as x approaches 1. 1 is our point of interest, but then we've got something else to consider. We need to consider the direction. Okay? So as we approach 1 from the right, so as we approach 1 from the right, what do the function values approach? Also approach 1. Okay? What if we approach 1 from the left? So we're approaching 1 from the left. What do the function values approach? Also 1. Okay? As we approach 2 from the right, so as we approach 2 from the right, we'd be up on this little horizontal line right here, this little segment right here. So what do the function values approach as x approaches 2 from the right, from the positive side? They approach 3. And what about from the left? That's going to be a 2. As we approach 3 from the right, that's going to be 2. And as we approach 3 from the left, that's going to be 3, right? Okay. Does everybody see what we're doing? It's pretty easy. Okay. As we approach 4 from the right and the left, what do we get out of both of these? We get 3 on both of them. What if we approach 5 from the right? 5 from the positive side. 5 from the positive side. There's no answer there, so we're going to use this. We're going to say DNE stands for does not exist. Okay, because the function's not defined there. Function's not defined there, so it doesn't exist. The limit does not exist. What about 5 from the left? That's going to be a 2. Okay, now, again, I want to point this out. Please note that g of 1 G of 1 is 3. Does that change your answer to part A above? It doesn't. Okay? It does not. And why not? Yeah, that's at the function. That's not what's happening around there. So remember where it said exists at the points around A, except possibly at A, at the point of interest. As far as limits go, we don't care what's happening on this one right at 1 in this particular case. We care what's happening around 1, okay? Now, when we normally find a limit, it's a two-sided limit, and sometimes we'll say the limit. We'll kind of emphasize that. The limit can't exist. The two-sided limit can't exist unless the two sides, from the left and from the right, agree, okay? Or we could say are equal. So we could go through here and we could say, you'll notice that down below, I've got an example here, 3 star. I've got the two-sided limit of each one of these for 1, 2, 3, 4, and 5. Well, let's just go through here. Do they agree? Yes. For 1? Yes, they do. So the limit would be 1. Do they agree for 2? No. They don't. So this is D and E, will not exist. What about for 3? Nope. So that'll be a D and E. And what about for 4? Yep, that's going to be a 3. And what about 5? Okay, one of them didn't exist, so the two-sided limit can't exist. So that's going to be a D and E. Okay, we'll come back to this one in just 1 second. Okay, now let's look at the picture. Does it agree? Do we have a limit as x approaches 1? A two-sided limit? Yes, we do. Do we have a limit at 2? Nope, we got this little bump right here. Same thing at 3. What about at 4? Does it exist? And it's equal to 3. And we know that at 5, there's not a two-sided limit. There might be a left-sided limit, okay, a limit from the negative side, but not one from both sides. And the last one right here, what's the limit as x approaches 0 from the positive side, from the right side, for this particular function right here? Happens to be 0. Okay, pretty easy if you're given a picture, right? Yeah.
Okay, so for E, we put a D and E, but for 0, why can't we put it at 0? Because it's not coming from the left side.
Because notice this is a two-sided limit, and that's a one-sided limit.
Oh.
Okay. Little details there. Okay, any questions? Okay, let's take a look at the next little bit, because it's pretty easy to tell, just by looking at a graph. But if you've got a function, if you've got an expression that you're trying to find the limit for, it's a little bit more difficult. There are a couple techniques that you can use. You can use analytic techniques. That means paper pencil, okay, working it out mathematically. You can use graphic or numeric techniques, and that's usually going to involve a calculator or computer. Okay, but if you do use a calculator or computer, remember it's just going to make some estimates. Okay, unless you've got one that has a computer algebra system that it can actually manipulate things. Okay, you got to be really, really careful, because calculators and computers can hide some interesting behavior just based on the algorithms that they use to figure things out and stuff like that. Okay, so make sure you're careful if you're using a calculator, like we were. Check the accuracy. And different things like that. And be aware when you look at a function, does it have any domain issues? Are there any things that I'm going to need to be careful with? So let's take a look at this problem right here. So here's the function, happens to be a rational function. That might just ring a bell in your head and say, oh, we might need to be careful here. But let's find the limit as x approaches 0 for this particular function right here. Well, let's see. If I'm getting really close to 0, that's getting close to 0. What would the denominator get really close to? Okay, it would get close to, it's going to be a positive 1. Okay, because 0 plus 1. Okay. And the numerator, this would be 0. That would be 0. Top would be getting really close to 4, so we'd think the limit would be 4. And it is. Nothing weird happens on that. Limit as x approaches 2. Let's see, the denominator would get really close to 3, and the numerator, this is going to be a 4 plus a 10, so we get 18, I think, there. So the top's going to get really close to 18, the bottom's going to get really close to 3, so the answer is going to get really close to 6. That's going to be the limit, okay? And then we run into something here. What happens when this gets really close to -1? Yeah. Yeah, okay, so the closer you get to -1, there's some weird stuff that happens at -1, so we've got to be a little bit careful, okay? So, here's how we do a problem like this. Let's factor this. This would be, let's see, multiplies to be 4, combines to be 5, so that's going to be +4 and +1, and the denominator's a +1. Now, what can I do with this? I can cancel this off, okay? Now, if that was a 0, I couldn't cancel it off. But the only time this is 0 is when I plug in a -1. Okay? And I'm never interested in actually plugging in a -1. I'm just interested in what happens around particular points, and -1 happens to be one of them. So as long as I don't actually plug in a -1, this, what I've canceled, is just a 1. It's the equivalent of a 1. They're the same number. So what we're doing here is we're finding the limit as x approaches a of this right here, that simplified expression. Those two things are equal. So what would happen if I plug a 0 into this? Yeah. It's a line that crosses at 4, so the answer's 4. Okay? Nothing weird happens on this one except for right there. There's a hole right there. And if I plug in a 2, or if I get really close to 2, this is going to get really close to 6. Could I find the limit here? Yeah. What do I get when I plug in a -1? I get a 3. So if we were to graph this, this hole is located at -1, 3. That's where the hole is. Do we care that there's a hole right there at -1? Does that affect what the limit is? Nope, because we don't care what happens right at -1. We care about what's happening around here, and everywhere else, it behaves like this nice little line, this nice little linear equation for x + 4. Okay, any questions? Okay, let's take a look at another one. This is a bit of a weird function. Look at that for just a second. I'm going to type that into the calculator and see if you can figure out what this is going to look like. Any ideas? Got some asymptotes maybe? Good guess. I need to turn this one off. Looks like it just does this. Okay, I'm going to change the window. I'm going to go from -1 to +1 in the x. Because does everybody agree that the interesting part of this, the interesting behavior, is where we're trying to find the limit at 0? This is -1 to +1. Okay. Change the window one more time. If the interesting behavior is happening at 0 and we're trying to find the limit at 0, we want to check the behavior on both sides of 0. So let's make this really small. Let's go from -0.1 to 0.1. This is a tiny window. This window is only 2/10 wide, and we're still leaving it from -3 to 3, so about 6 tall. So let's hit graph. Let's watch what happens here. And I'll do it one more time, and let's go from -0.001 to +0.001. Okay, so here's what it does. Okay, kind of just lazily goes up and down until it gets close to 0, and the closer it gets to 0, the more it does like this. Now, does everybody agree that you can't actually plug a 0 in here? So it's got to be undefined right there. And then on the other side, it does something similar. And what happens is, it just continues to oscillate back and forth on both sides. Okay? Just goes like this. Back and forth, back and forth. The two sides never connect. What? There's not, and it doesn't, I don't even think it does this together. I think it does that. Okay? So if the limit is, do they approach the same thing from both sides? Does this approach the same thing from both sides? Let me ask you this. Does it approach anything from either side? We're talking function values here. If you've got something that's just going up and down from -1 to +1, does it ever stop? Does it ever do this and settle down on one particular value? No, it just continues to oscillate, okay? So on something like this, that limit does not exist. Okay. So now I'm hoping from your pre-calculus knowledge, because graphs like this need to be recalled pretty quickly, you should know what this looks like, and you should know what this looks like. So 1 over x looks like this, and 1 over x squared looks like this. Now, those two functions are a little bit different than the other functions that we've seen so far, all the pictures that we've looked at, because they've got asymptotes. They've got places where probably the most interesting behavior on both of these is at 0. Okay, on this side it goes down toward -infinity, on this side it goes up toward +infinity, and on this side it goes toward, up on both sides. Okay, got a vertical asymptote at x equals 0 on both of them, but that type of behavior is kind of interesting, so we want to study it a little bit further. And if you know those types of graphs and understand this type of behavior really well, you're in better shape for what's going to come down the road, not only in this section, but in a couple sections ahead. Okay, so we want to look at definition number 4, and it says this: let f be a function defined on both sides of a, except possibly at a itself. Again, why don't we care about a? Why can it not exist at a, and that's still okay? We want the activity around there. We're not interested in what's happening right at a. That's why it doesn't have to exist there. Okay? And it says the limit as x approaches a of f of x equals infinity means that the values of x can be made arbitrarily large, or in other words, as large as you want, by taking x sufficiently close to a, but not equal to a. So what it means is, as the closer you get to a, the bigger the function value is. Okay, that would make the limit equal to positive infinity. Okay, and if we say this another way, and mathematicians use this phrase quite a bit, we say the function increases without bound. It means the function values get larger and larger and larger, and there's no limit to how big they can get. Okay, if that's the case, the limit is positive infinity. So if they increase without bound, get larger and larger and larger without bound, we say the limit's positive infinity. What if it decreases without bound? What would the limit be? It would be negative infinity. Okay, and there's a definition for that in your textbook. Okay? I didn't feel the need to put them both on there. Okay, they basically say the same thing, but in other directions. Okay, so we're going to compute what the limits are for each one of these. You'll notice that for a, b, and c, we're using this function right here. We're using the reciprocal function. And for E, F, and G, we're using the reciprocal square function. We're using that one right there. And graphically, you can look at it and you can tell what's going on here. Okay, on this one, it's talking about the limit as x approaches 0 from the negative side, from the left. So as x approaches 0 from the left, what happens to the function values? Okay, answer is going to be negative infinity. Okay. What if we approach it from the right? That's going to be positive infinity. What about the two-sided limit?
Does not exist.
Okay, does not exist because the two sides don't agree. Okay, now, I need you to think of this in more than one way. We just looked at a picture. This is going to be a really valuable technique. If you understand what I'm talking about here and represent it this way, I think you'll be able to do some of the much more complicated problems, not only now, but the ones that we're going to encounter in the future, and they're going to make a heck of a lot more sense. Because it's going to get way more complicated than 1 over x and 1 over x squared. Okay? So here's the way I want you to think of it. Okay? On the problem up above, this guy right here, we were kind of looking at it and say, what does the top get close to and what does the bottom get close to? So the closer we get to 0, the closer the top gets to 4, and for the bottom it was getting close to 1. Never actually equaled 4, never actually equaled 1. But we kind of make that argument. Okay, I want to do the same thing here. Now, the top is the number 1. Does that ever change? It doesn't ever change. The only thing that changes is the variable in the limit, and the variable in the limit is x. So we're going to write it down this way. The top is positive and I'm going to use an arrow, and it's approaching 1. It does actually equal 1, but we're going to keep track of the sign and the numeric value, how big the number is, separately, and you'll see why by the time we're done here. Okay? So the top is positive, write down the sign, and write down what number it is or what it's approaching. Okay? Now, the bottom. The bottom is an X. What type of X's are we plugging in? Negative X's. Okay? So the bottom is going to be negative and approaching 0. Now, to find the answer, figure out what the sign of the answer is, and then consider what type of quantity you've got. The top is positive, the bottom is negative. What's a positive divided by a negative? It's negative. Now, let's figure out the magnitude. Let's figure out the size of the number that we're dealing with. We're taking a number, the number 1 in this case, and we're dividing it by something that's getting smaller and smaller and smaller. What happens when you take a number and divide it by something that's getting smaller and smaller and smaller? It gets bigger, right? So it's going to be negative infinity. Let's do the same thing on this one. The top is positive, and it is 1, or approaching 1. Let's look at the factor on the bottom. The bottom is an X. We're plugging X's that are positive and getting really close to 0, getting really, really small. So the sign of the answer is positive. What happens when you take a number and divide it by something that's getting smaller and smaller and smaller? It gets bigger and bigger and bigger. Okay? And since the two of these aren't the same on either side, since the left side doesn't agree with the right side, then the two-sided limit wouldn't agree. Okay? All right, let's figure out this one without looking at the picture, even though it's right there. You know what the answer is. Okay? The top is positive 1. What about the bottom? The bottom is going to be a number squared. You can figure out the sign without even knowing where we're finding the limit. The bottom is going to be positive, and we're plugging in numbers that are getting smaller and smaller and smaller. What happens when you square a number that's getting smaller and smaller and smaller? It gets, very well said, it gets smaller faster. So these are still going to 0. Okay? So the answer is going to be positive. And if I have a number divided by something that's getting smaller and smaller and smaller, it's going to be positive infinity in this case. Okay? If we look at the picture, does that increase without bound on the left side? Yes, it does. And if you take a good look at this and think about it for a second, when we work this out, it's going to be exactly the same thing because the top is a positive 1. The bottom is squared, so it's going to be positive. And it doesn't matter whether we're plugging in positive numbers or negative numbers that are getting close to 0. The bottom's still going to be positive and approaching 0, so we're going to get positive infinity. Okay? Any questions?
Isn't the bottom approaching 0?
Oh, sorry. I think I said that but wrote it wrong. Okay? So, what's the limit as x approaches 0 if we say it's a two-sided limit? Okay, then we'd say it's infinity. Okay. Now, I know that might seem a little bit silly, but this is going to be a really important technique in this chapter, so it's a good one to think about. These are very simple examples. You'll find mathematicians that will say infinity is more of an idea rather than a limit. So there will be a lot of people that will say, look, if it's doing this, say the limit doesn't exist. Okay? So there would be people that would say that's, these aren't valid answers for what the limit is. You should describe that it increases without bound or decreases without bound. I like these. I say this all the time, that it's negative infinity or positive infinity. And this is a really good example of, it describes the behavior on both sides. Saying that the two-sided limit is positive infinity describes what's going on the graph. And saying that the limit does not exist, you can see that those two sides don't agree. Okay? Any questions there? Yeah.
So would you suggest this doing the numerator and denominator for each problem for the homework?
It depends on what it is. If it's a rational expression, we're going to see some examples in just a second, and I think you'll see what I mean. Okay? So, in definition 6, they talk about a vertical asymptote. All they're doing here is, you already know what a vertical asymptote is. They're just describing it using calculus. So it says the line x equals a is a vertical asymptote of that curve if at least one of the following statements is true. that the limit is positive infinity as you approach it from both sides, from the left side or the right side. So if it increases without bound from either the left or the right or both sides, that's going to be a vertical asymptote. And the same with if it decreases without bound. Okay? So if we look at this one right here, so on this picture right here, this is the point 1. The limit as x approaches 1 for this particular graph is, well, what does it approach from the left and what does it approach from the right? Positive infinity. That means x equals 1 is a vertical asymptote. What does it approach? What's the limit as x approaches 3 from the negative side, from the left side here? Negative infinity. That means we don't even have to check the other side, but that means at x equals 3, we've got a vertical asymptote. So both of those would be vertical asymptotes. Okay? If we check it over here, if we check the behavior from the right side of 3, it's going to be positive infinity. Does it matter that the two of these don't agree? It doesn't matter. It does for the limit, but not for the vertical asymptote. As long as either one of those are positive infinity or negative infinity, you're going to have a vertical asymptote at that point of interest. Okay? And by the way, remember, if these two don't agree, that's not going to exist. Okay? Any questions? Okay. You're not always going to be given a graph. There are some problems on the assignment where they'll give you a picture and it's pretty darn easy to tell. Okay? So if you're not given a graph, you've got to be able to find the answer analytically. Okay? And this is where that idea that I talked about a second ago is important. So let's take this example right here, and we want to find the limit as x approaches 3 of 2 over x minus 3 quantity squared. Well, you could take the time to graph that or transform the reciprocal square graph, or we could consider this. Let's use that technique that we were dealing with before. Does the top change at all? Nope. So it's positive 2. The bottom has the variable in it, so it does change. Notice that the entire denominator is squared. So what can you tell me about the denominator? It's going to be positive. Okay? And the closer we get to 3 from either side, the closer this number gets to 0. So it's positive and approaching 0. What's the sign of the answer? Positive. Number. Who cares if it's 1 or 2 or 17 or 400? If you take a number and divide it by a number that's getting closer and closer to 0, what happens to the overall quantity? It gets big. So there is the limit on that one. Didn't have a picture or anything. We're just relying on the behavior of the functions. Okay? This one's different. Approaching 0 from the positive side. Approaching 0 from the positive side. So if you have any trouble figuring this out, just pick a positive number that's really small, really close to 0 from the positive side. So let's say I plug in 0.1. What's the sign of this numerator? Negative. A number really close to 0 minus 2 would be negative, and it's going to get really close to 2. It's negative and getting closer and closer to 2. What about the bottom? We're plugging in positive numbers. What's the square root of a positive? A positive. So that's positive. And getting really close to 0. What's the sign of the answer? Negative. And a number divided by something that's getting closer and closer to 0 is larger and larger. So that's going to be negative infinity. Okay? What happens at x equals 0 if we were to graph that? Right at x equals 0, it's undefined. What else? What could you tell me about around? What would x equals 0 be on that graph? It would be a vertical asymptote. Okay? Because here's what we know. I haven't graphed this. I don't know what this looks like. I know it doesn't exist for negative values and it doesn't exist for 0, but what I do know is if you were to graph this, it's going to have a vertical asymptote. It's going to decrease without bound as we approach 0 from the right side. Everybody good with that? I haven't graphed this. We could pretty quickly. I'm hoping you could anyway. But what I do know is that if I go to x equals 3 on that graph, what am I going to have? I'm going to have a vertical asymptote there. And what's the graph going to do on either side of it? It's going to increase without bound. I may not know what any of the rest of the graph looks like, but it's going to look like that around x equals 3 because it's a vertical asymptote. We know that it increases without bound on both sides. Yes?
On V, why is it approaching 2 on the numerator?
Okay, so x is getting closer and closer to 0.
Yeah.
So this is getting close to 0. So if I take a number really close to 0 and I subtract 2, it's going to be negative and it's going to get really close to 2. Okay? The thing you need to keep straight is, the top is really, it's going to get close to negative 2. Okay? We could write it like that, but what I found over the years is if you keep the sign separate from the size of the number, it's easier. Good point, good questions. Everybody clear on that? Okay. It wouldn't be good if you did this. If you said it's negative and approaching negative 2, it wouldn't work that way. And for a lot of people, because then it's not just going to be a number, it's going to approach that number. Does that make sense? Okay. Okay, let's look at this one. Any ideas here? Yeah, the closer it gets to 5, it's going to be 0 on the top. And what about the bottom? Also 0. So here's what we run into. This technique right here relies on the fact that we've got to have everything factored. So let's take a look at this one. I can take out a 4. I'm left with t squared minus 25. I can factor that to 4, t minus 5, and t plus 5. Oops, let me slide this over. And the bottom is t minus 5. What can I do because I'm never actually going to plug in a 5? Cancel those off. That gets really close to 4. In fact, it is 4. And this gets really close to 10. So what's my answer here? It would be 40. Does that make sense? Any questions? You're sure? Yeah, Ben.
On the first limit, the A,
Yep.
you put on the bottom that it's positive going to 0.
Mm-hmm.
Why isn't it going to 0?
Because we're approaching 3. X is approaching 3. We're plugging in numbers that are getting really close to 3 from both sides. So if I plugged in, again, thank you for the questions. I want to make sure everybody's clear on this. Okay, if you can't make sense of the idea, plug in a number. This says we're plugging in numbers that are getting really close to 3 but not equal to 3. So plug in a 3.1. 3.1 minus 3 would be 0.1. 3.01 minus 3 would be 0.01. Okay, and the same with if I plugged in 2.99. This would be 0.01. Square that, it's going to be positive and it's going to be even smaller.
It's getting close to 0.
Getting close to 0. Everybody understand there? Okay, really important to clarify those details. Okay, let's take a look at this one. It says, describe what happens to each factor of the rational expression as x approaches 3 from the positive side. So let's take a look at this. As I approach 3 from the positive side, so I'm plugging in numbers that are really close to 3 from the positive side. So give me an example of a number I could plug in just to make a numeric computation here.
0.29.
Okay, 0.29 would work. 0.29 minus 2 is 0.9.
Aren't you coming from the right side? So when you want to do
Oh, yeah.
0.9,
Oh, we do want to come from the right. Yep. So let's do 3.01. Okay? 3.01 minus 2. Positive 1.01, right? And the closer we get to 3 from the positive side, the closer this gets to positive 1. You with me there? Okay, that's the factor on the top. Let's do this factor. Without even plugging anything in, can you tell me something about that factor right there? It's going to be positive, okay? So it's positive, and it's approaching, let's see, what if I plugged in a number really close to 3? That would be about 3 minus 1, about 2, and square it, so it's going to be about 4. You with me? Okay, let's look at this one. What happens when I plug in numbers? Let's use 3.01 again. What if I do 3.01 minus 3? 0.01. Is it positive or negative? positive, and approaching 0. Okay, see how I said it would get more complicated? Okay, now let's look at the sign of each one of these three factors. Positive, positive, positive. What's the sign of the answer going to be? Positive. This is a number. This is a number times 0. Well, which one's going to win on the bottom? Is the 4 going to win or is the 0 going to win? The 0 is going to win. We're going to have a 0 in the denominator. So this is a number divided by a number that's getting closer and closer to 0. So what's my limit? Positive infinity. Okay? Is everybody clear on how you can figure this out by keeping the sign separate from the number? The magnitude of the number? Everybody good there? Okay. What does that mean happens at x equals 3? We have a vertical asymptote. What does that mean about the behavior of the function on the right side of 3? Goes up. Increases without bound. That would be a nasty function to graph, but we already know part of the behavior. You with me? Okay, let's see if we can do this one a little bit more quickly. If I'm plugging in a number that's close to 3, but from the negative side, so from the left, so a little less than 3, isn't this still going to be positive and approaching 1? 2.9 is going to give me 0.9. 2.99 is going to give me 0.99. You with me? What about this one? What's its sign? It's squared, so it's still going to be positive. The closer I get to 3, the closer this quantity is going to get to 2, and I'm going to square it, so it's still going to get close to 4. Doesn't change either of those because they're not the interesting factors. There's nothing interesting about either one of these when we're plugging in something close to 3. It's this one that causes the interest to happen. If I plug in a number a little less than 3, what's the sign of this factor right here? Negative. And what is it approaching? What number is it approaching? Approaching 0. What's the sign of the answer? Negative. Limit's going to be infinity. What do I know happens to the graph as we approach 3 from the left side? Goes down like this. Okay? Any questions? Okay, now, here's the cool part. You don't need to flip the page over. That's that one right there. And here's a picture. So we've kind of looked at this one both ways. And did we end up with the right behavior by thinking about it the right way? By thinking about the sign and the magnitude of each one of those factors. Any questions? Excellent. Okay, let's take a quick look at these last couple. You've got problems like this in your textbook. It says, sketch the graph of an example function that satisfies all of the given conditions. If they tell you what a function value is, those are the easiest things to do. So let's work backwards on this. F of 0 is 1. F of 0 is 1. The limit as x approaches 0 from, you could do either one of these, I suppose, 0 from the right side is 2. So I don't know anything about the behavior of the function out here, but I do know as I get close to 0 from the right side, what does it need to approach? It needs to approach 2. Okay? So somewhere around there. I'll come back and, well, let's see. Is there any way that could be a solid circle on the end here? Not and be a function. They told us it was a function. The limit as x approaches 0 from the negative side, so from the left side, is -1. So I have no idea what it looks like over here. Could be all sorts of weird stuff, but I do know the closer I get here, closer it gets to -1. So there's -1, there's 1, there's 2. That's an example graph. Okay? Any questions? Okay. Could you do these? The stuff we just got done doing is way harder than that. Okay? This is a simple factor on the top and the bottom. Okay? Just ask you to figure those out. What would be the limit in each of those cases? Okay? Any questions? Okay. Let me